Welcome back. The first speaker this morning is Ivan Kostov, and he's going to tell us about integral models on a torus. Thank you.
Thank you. So let me first thank to Filippo and the other organizers for setting up this remarkable conference. And well, today I will speak. Well, it's a little bit out of the main topic of the conference, but there is some relation because I will speak about gas of interacting loops. Closer, like that. So it is known for a long time that the infinite volume thermodynamics can be formulated exclusively in terms of the S matrix of the scattering data, and this is known since '69. This paper, sorry. Where is the light? At the very. No battery?
Why not? Well, maybe.
Oops.
This is the Roman Empire falling into pieces.
Okay, I will try to point by with the. Pointer? Oh, yes, like that. I don't see it. It's. Well, no, I think that it will be. I can pass without. So. Later in the 90s, Alyosha Zamolodchikov revived the thermodynamic Bethe-Ansatz in a sense, and he showed that the finite volume effects in two-dimensional integrable models can be computed by using the TBA and in the Lorentz invariance of the system. I will address the question, is it possible to generalize this description to the case of the torus when you have not only a long cylinder, but you have a periodic rectangle with two finite periods? And the answer is, in principle, yes, because the TBA allows one to compute in principle, the full spectrum of the theory. This is an horrible exercise. In practice, it's impossible, but in principle, you can do it. After summing over all excited states, you will have the torus partition function. But for the moment, nothing is known about that. Only the torus partition functions of conformal field theories were computed because of the huge symmetry, and also in a couple of generalized free theories, as the free Gaussian, free massive boson or fermion, and also the Ising field theory. So in this talk, I will defend the following claim, which will be the basis of the manipulations later, that the torus partition function is the sum of the partition sum of a gas of loops embedded in the torus with interaction which is defined by the scattering matrix of the theory. And once you assume that, I will try to defend this claim. So once you assume that, then you can do the following. In this gas of loops, you can decouple the two-body interaction of loops by kind of Hubbard-Stratonovich transformation by introducing extra auxiliary field. And then this means that you have a gas of loops in a bath of some extra, external field. You can sum up over all loops like they were if non-interacting, and then you obtain some effective potential for these Hubbard-Stratonovich fields, which allows you to set up a perturbation technique. In particular, the limit when one of the periods is very large is a kind of mean field theory limit where all the loops, all the cycles in the Feynman diagram technique disappears. And so this, as a byproduct, this is a proof of the, not proof, but a derivation of the thermodynamical Bethe-ansatz. I will consider only the simplest theory with one single particle and no bound states, like the Stinge-Gordon model. So the idea, first, the first thing to do is to compute the sum over the loops on the torus, first without any interaction. The sum over the loops can be split into sum over topological sectors, which are characterized by winding numbers. W and W prime are the numbers the loop winds around the first and the second period of the torus. So this, the sum over the loops in one topological sector can be computed by taking the path integral over the loops and introducing a discontinuity at some point. This discontinuity should be proportional to the frustration along the two cycles. That is, this delta x should live on the period lattice of the torus. So summing over all possible discontinuities of loops introduces the periodicity, the double periodicity in the torus.
Ivan?
Yes.
So these loops, should we just think of them as the world lines of particles?
Yes,
So,
exactly,
okay,
yes.
yeah.
So we start with with a Lorentz invariant massive theory with some scattering matrix. So the particles are described by a path integral of the world line of massive particle. Yes, but of course you can sum over the loops by applying the Polyakov quantization of particles, integrating over the proper time. But well, this I tried to do it at Saclay once, and it took all the time. All the time of the seminar. So I will not repeat it. I will do something different. So we know that the integral over one loop is log det of the Laplacian. Yes. So I just take log det of the Laplacian, and I say this is the integral over one loop. But just I insert this discontinuity delta x, which belongs to the period lattice of the torus. And when you go to when you diagonalize the Laplacian, you go to the momentum space. This is just this simple integral. And once you compute this integral, which is kind of Bessel function, you can sum over all winding numbers to obtain the free theory, the free energy on the torus. So I will do something different, not explicitly computed this integral, but taking one of the integrations. Say here I integrate it over the second coordinate of the momentum, k2, and if you do the integral by residues, you obtain this single integral already. So this is something which is familiar. This is the wave function of a massive particle in Lorentzian theory. I mean, on mass shell particle in massive theory with in the infinite Lorentzian space. Sorry, Poincare space. This allows one to treat it as a scattering particle and to implement the scattering data. So we can do this, but we can do also integration over the first component of the momentum. And then we also can interpret this as a world line of particle moving in the time, but the role of the time is of the time coordinate is different. So here in the upper line, you have analytical continuation from the second coordinate. So the time is obtained by Euclidean rotation of the second coordinate, x2. And so this is small delta, it's not big, sorry. And in the second case, it's the opposite, the first coordinate. So you can imagine that there are two particles that one is evolving vertically, say, and the other horizontally on the torus. So they have different kinematics. And usually in the scattering theory, you speak about the direct and the cross channels. These two are related, these two descriptions are related by the mirror transformation, which exchanges the energy and the momentum, or time and space in the Euclidean theory. So this is the double Wick rotation. And here and in the following, I will use this parametrization of the momentum and the energy of the massive particles with the rapidity theta. So this parametrization implies the mass shell condition, E square minus P square is equal to M square. So now when we fix the discontinuity delta X to be on the weight lattice of the torus, on the period lattice of the torus, we have two descriptions of the sum over winding loops on the torus with winding numbers W and W prime. This is not tilde, this is prime. One is a particle for which the time is in the along the L cycle, so we call it physical kinematics, and the other is when the time is taken on the R cycle, and we call it mirror kinematics. Of course, these two descriptions are equivalent, and the two integrals are equal, and this can be checked. They are obtained by the same expression, but also this can be transformed. One can be transformed into the other by analytically continuing the contour of integration. So when we sum over the loops, we can use either of these descriptions at will, and in this way we can we can write different expressions for the free energy on the torus for the free theory, say? And they will be related by modular invariance. We exchange the R and L cycles. For the moment free, yes. But I will introduce the interactions later. First, let us check that this description works for the free theory. So I take the partition function of the free massive boson, and since the loops in the free theory don't interact, the free energy is just the sum over one single loop. And it is equal to sum over all possible winding numbers, positive and negative and zero. And it contains the first term, which is loops without any winding. So this sum is divergent. This is the contribution of the infinite volume, when we have infinite volume, and this gives the infinite volume energy density, which is infinite also. And then we can organize the sum in this way. We sum over the winding loops in the physical kinematics, the second term, and the sum is for W non-zero. And the second winding number is zero. And then we sum over the loops in the mirror kinematics when the W prime is non-zero and W is whatever. So in this way, we exhausted all possible windings. But it's important that when one of the winding numbers is zero, we have to choose the kinematics on the other directions. Otherwise, it's not well defined. So that we have W's in the denominator. So now we can just sum, because the amplitudes for the loops are very simple. We can sum explicitly over the winding numbers, and the result is this integral. So the two terms of this integral, I mean, I just use these abbreviations for these sums with factors depending on the. So you have. Let me remind you. You have 1 over W here for W, but for W prime sum you don't have this one. So you have two ways to sum over the loops, with this one when you have 1 over W and this without. So the result is this: the sum of two integrals. The first integral is linear. This corresponds to the second term here with f. And the second integral is a contour integral around the real axis. So this corresponds to this second, to the sum over the dual, or over the mirror world lines. So the first function comes like in this term, by sum over windings in the time direction. And the second one is because you have a second winding number, and this one can derive it most directly by noting that the second sum is just the periodic delta function, and the second factor is just the analytic expression for the periodic delta function. You have two poles on both sides of the real axis, and when you make the contour integration, you pick the sum over the values of the integrand, which are 0 up to 2 pi n. And so now, to check that this works, let us perform the contour integration in the second term. So the first term is well known. This is the Casimir energy of the free boson, which is given by this integral. And the second term is some infinite sum of terms, which when you take the exponent of the free energy, will give a product of, will give just the partition function of free oscillators. So it works for the free boson. Now let us go to the scattering theory. And this is a flash of what is theory with factorized scattering. So here you have a scattering matrix which factorizes into 2 particle scatterings. It satisfies these 4 restrictions: unitarity, real analyticity, crossing, and also you have to choose for 0 rapidity. So for 0 distance of the rapidity, by unitarity, it's either 1 or -1. So both cases are possible, and this is the sign is called the TBI statistics usually. So the transformation between the physical and mirror kinematics is just theta is going to I pi divided by 2 minus theta. So this analytic continuation in the rapidity space. And we will consider, on the torus, we have to consider scattering of physical with physical particles, mirror with mirror particles. So this gives the usual S matrix. But also, we have to consider scattering with physical with mirror particles. And this, by this transformation, will give this function W, which I will use later, which is the shifted S matrix. So now the logic is the following. So we describe the winding loops as loops with injected discontinuity. Then we analytically continue when to the domain in the, we say that delta x is equal to x minus x prime, and you continue to the domain where the particles are well separated, and we can consider them as scattering particles. Then you introduce these scattering factors between them, and then we analytically continue back to the period lattice of the torus. So this is not a rigorous statement, but somehow it justifies the procedure we did. So we, in the case of interacting theory, we have Gaussev loops as before, but they are interacting with this scattering factors W and S, depending of their kinematics. And so here I take an arbitrary combination of n loops with physical kinematics and n tilde loops in the mirror kinematics. So this is clear, the third line is clear. And the second line is this is f of 0 to the power, to some power, which depends on the winding numbers. And this is because a loop with, which winds around the cycles of the torus can intersect itself a number of times. And so this counts for this intersecting. So now the next thing is the integration measure. So the integration measure is assumed to be the flat measure of the phases of all matrices. I mean the phases of the semi-classical wave function when you go around. I mean, which correspond to the discontinuities introduced before. And in the free theory, we had only this term. But in the scattering theory, the phase depends also on the scattering phases when the particle meets all other particles when making a tour around the world. And we have these two terms from scattering with the physical particles and physical with the mirror particles, and vice versa. So to express this measure in terms of the rapidities, we should introduce a Jacobian, and this Jacobian is the celebrated Godin determinant. Which in terms of, which in the case of the torus, it is 2x2 block determinant. So now, we want to sum up all the loops. So we will do the following trick. So we introduce two auxiliary fields, phi and phi tilde, which are associated with the two cycles of the torus. And we say that the two-point function of these fields is the scattering factor between the physical and the mirror particles. And their expectation values are the bare phases along the time and the space circle of the torus. So this is, however, not sufficient because we have the measure. And in order to count correctly for this Godin determinant, we have to introduce Fadeev-Popov ghosts for the measure. And these are fermionic particles with the same correlation function, this one. In terms of these fields, the loop amplitude with given winding numbers become operators. And this is the expression I wrote before, but instead of these classical phases LR, LE, and RP, I write these fields. And also the integration measure contains all the derivative of phi and the bilinear combination of the ghost fields. It smells supersymmetry. Actually, in the limit of TBA limit, we have supersymmetry, but not in the general case. So now we can write the contribution I wrote before of scattering particles, n and n tilde scattering particles, by the expectation value of a product of these operator loop amplitudes. So in doing that, we can very easily sum over all winding numbers, as in the case of the free field. So we do it introducing these functions, polylogarithms with negative indices. So the first is just usual logarithm, the second is this one, and the third is that. So when we sum over the winding numbers, we obtain the following effective action in terms of the auxiliary fields. So we have this effective potential, we have the expectation values of these fields, and you have the two-point function. So everything is well defined, and in this sense, the field theory on the torus is given by this expectation value of these auxiliary fields. So now this can be written in more explicit way by expanding the auxiliary field in modes. So there are free fermions and bosons. We can use the expansion of the function W, the shifted test matrix, in the exponent of the rapidity, and then introduce these two sets of bosonic and fermionic oscillators. So the A operators are associated with one of the cycles of the torus, and the A tilde operators with the dual cycle. We have these simple commutation relations. So the S matrix is implemented in the commutation relations of the bosonic and fermionic modes. And with this definition, the torus partition function is given by this expectation value. So this is interaction potential, and these evolution operators here, which change the Fock vacuum, they introduce the expectation values we had. They introduced well the expectation values of the auxiliary field. Sorry. Yes, this one and this one. So the interaction, sorry. The interaction doesn't depend on the geometry of the torus. Only these two factors that turn the Fock vacuum depend. So this resembles a bit a tau function, but it's not a tau function. Now I have 7 minutes. For 10. Oh, thanks. Then let me give an example, the Singe-Gordon model. So for the Singe-Gordon model, it's given by this Koch interaction potential with this constant B here. So the S matrix for the Singe-Gordon is given by this expression with alpha related to B in this way. And the logarithm of the W function, the shifted S matrix, is expanded in this way. So Wn are this cosine of, well, Pn A divided by 2. First remark is when you write this partition function on the torus, I didn't normalize it. In general, you have to divide by this expression in order to have no dependence on the area of the torus. I mean, the term which is R, L, and something. But if you don't normalize it, the result is exactly the free energy of the infinite volume, which was computed by Destri and De Vegge long ago, using the prescription that the exponents in the potential are normal ordered. Second remark is that on the torus, you can write, for this field theory, you can write a word identity which resembles the Y system for the theory on a cylinder. But the difference is that here you have not, you don't, this is not a function, but this is expectation value of this function of the operators. And you will have corrections to this classical expression, which is given in the cylinder limit. So let me tell some words about the cylinder limit, which is the TBA, the limit also. So this can be considered as an alternative derivation of the TBA prescription, of the TBA equations. In the limit when R is very large, the interacting potential becomes quite simple. So this is just these two terms. Only linear integral, no contour integral. And then you if you consider the diagram technique, well, I will show it later. The diagram technique for this potential, which is non-polynomial potential, but it has the field phi tilde is linear in the interaction. So if it's linear, sorry. If it's linear, then the theory, the perturbation expansion of the theory stops, and one loop. Not winding loop, but one loop in the perturbation theory. So we cannot make more complicated diagrams than this one cycle. Moreover, since we have bosons and fermions with the same propagator, we have bosonic and fermionic loops which cancel completely. So the theory becomes a theory of trees, no fluctuations at all. And summing these trees is just a mean field theory problem. So you sum that by a nonlinear equation, which is in this case the TBA equation. So we have you can derive a simple word identity in this theory, which is the TBA equation for the pseudo energy, the expectation value of phi, and also another equation for the expectation value of phi tilde, which is this one. I mean, the integral is with the scattering kernel, which is the derivative of the two-point function. So the relation with the TBA is that this epsilon is the logarithm of the Hall and the particle densities, the ratio between the Hall and particle densities, and the derivative of the second field, its expectation value is R times the sum over the two densities. So this second word identities corresponds to the beta equation in terms of densities for the TBA. So I'm close to the end. So here I just drew some pictures about the diagram technique for this effective field theory. If you expand the potential at 0, which is not the best thing you should do, but you can do it. So you have these vertices and propagators, and you can compose from them diagrams which don't have cycles, because the cycles cancel, and they have the form of trees. So this is the free energy. This is the diagram expansion for the free energy, and this is the TBA equation. So if you use vertices which are correspond to expansion of the interaction potential around the mean value of the fields, classical mean value of the fields, all vertices disappear, actually. And in this improved diagram technique, the TBA equation looks like that. The second identity is like that, the Bethe-Ansatz equations. And the free energy is this one integral and the contribution of loops which cancel. So that's the end. So I can just add some possible developments. But first, let's repeat the main message of this talk is that usually in the TBA calculations, you cut along the cycles, and then you introduce a complete set of states. And this leads to a laborious procedure, which when you have, say, infinite volume form factors, you have to compute the finite volume form factors from them by carefully regularizing and throwing out the infinities. So here in this formalism with loops, you don't need to do that. I mean, you obtain from the very beginning finite results. And well, if it's possible to generalize this procedure to non-abelian case, then it would be a good alternative to the standard computations of the using TBA. So what can be done is you can use this effective field theory to compute the exponential corrections to the TBA results. This is relatively simple. Then it's very interesting if this can be generalized for. No, this can be of course generalized to the purely elastic scattering theories. No problem. You will have several pairs of bosons and fermions, but it's not obvious how to generalize it to the non-diagonal scattering. And here, some analog of the nesting procedure should be worked out. So this formalism with loops can be very easily generalized to the case of the cylinder with open boundaries, finite cylinder with open boundaries. And now as a result, one will obtain not only a product of two G functions, but the free energy of such a cylinder will contain contribution from the boundary entropy, which mixes the left and right boundaries of the cylinder. Of course, when the cylinder is long, this is exponential terms that disappear. I mean, the interaction between the left and right boundaries disappears. The last thing is that one can try to compute the one-point functions on the torus. At least there are corrections for finite, for large but finite, say, R cycle by generalizing the Leclerc-Musardo formula. That is, in the infinite volume form factors, they will be attached to loops which can go through temporal, but also through the space cycle. And well, this is all. Thank you.
Thank you for a very nice talk. Are there questions?
Non-diagonal are complicated, but if you have a diagonal with phi cube, like Jan Gli, for example, do you think it is doable? It's not unitary, of course, but so still.
With phi cube, but what you need here is the S matrix. I mean, the potential is not at all used in this description.
Okay, sure. Because so you probably have loops with which, I mean, so join each other.
Ah, you mean
phi cube interaction.
Oh, you mean the theory with yes, with bound states which are
which are the same particle.
Oh, I don't know. Maybe it's possible. But
that may be interesting.
Oh, I see. I haven't worked on that.
Yeah.
Anybody else? So, is there any possibility of saying anything about higher genus using this loop approach?
About
higher genus.
Higher genus. Even on the torus, it's very complicated.
But for the simplest possible S matrix.
Well, maybe you can use such kind of similar construction in the case when you have A and B cycles on the surface, and if the A cycles are infinitely long and B cycles are finite, then you can count only the loops that go around A cycles, but they can have several possibilities. So maybe this could be a possible way to compute, but I cannot say anything concrete.
This is not a conformal field series, so it will depend on geometry of your surface. Yes, so even here it is rectangular. Yes. It's not. You cannot do real modular transformations, right?
Absolutely, I agree, Fedje. So here you don't have a conformal invariance. So the torus is, the torus is only rectangular. I mean, you can make it tilted, but it should be, you cannot change the variable. And the surface I thought about is the surface which is, for example, you have such kind of surface. You have one cycle. These are infinitely. 1, 2, 3 cycles. So in principle, you can apply that here. So the world sheet here must be, the particles should propagate without seeing any curvature. So there should be no curvature here. And in this case, we have two defects. So the particles will see these defects as operators. And actually in the ADS-CFT correspondence, this kind of world sheet describes a 3-point function of some operators, and this corresponds. This points to form factors, which are called hexagons, and so yes, we hope with Didina that. And perhaps Benjamin, that we can describe this configuration
And what about just putting defects into your original torus?
Defects will be seen by loops, yes, because
Yes.
the loop can wind around the defect and come on the right and on the left. So in this sense, they can be introduced. Like if you compute the one-point functions, you introduce a form factor, and the form factor, you can consider it as kind of defect. The loop can glue to the interact with the form factor and give a different weight to.
Okay. So,
clarification. Would it be conformal limit?
Yes.
On the torus? That will be described sort of ON model loops also, but in the limit,
ON model.
ON model loops, but in the limit, continued limit, it will be a Coulomb gas description, which is Gaussian field with the charged infinity. Okay. Now you have another description, also the same problem, but now with interaction through this matrix. So as far as I understand, it's a representation of Young partition function through the Gaussian field.
Yes.
So I would expect, and this is my question, that if you go to conformal field theory limit, which is specification of S matrix, not S matrix really, but equation of state, you're supposed to obtain, I would expect you may obtain just Coulomb gas description of conformal field theory, which is also Gaussian field with a background charge. Is this right?
Not so clear. Not so clear. There is some analogy. So first, these loops are in the rapidity space, kind of momentum space, some parameterization of the momentum space. I think that might be there is some relation between the results by Sergei Lukyanov and Sasha Zamolodchikov, where they consider the Sine-Gordon model and the Young potential of the Sine-Gordon model, which satisfies also some Singe-Gordon equation with some special boundary conditions. In some sense, there is some duality, and their Young potential must be related with this description, I think. Well, I try to see how it happens when you take the conformal limit of the Singe-Gordon model, and in this case, you have this expectation value which resembles a Toda tau function, and when the mass is going to 0, it splits into a product of two expectation values, one related to the right Fock vacuum and the other to the left. So in the middle, you introduce kind of projector to the intermediate states, which are very simple. It's, I mean, Alosha Zamolodchikov considered in an unpublished paper, actually Jürg Techner also, how to get the conformal limits of the Singe-Gordon theory. So this is Liouville. And you obtain the product of the sectors, right and left sectors of Liouville theory. So in the middle, so this is seen in this expression also, they are related by boundary condition, asymptotic condition for the I mean, which has to be introduced in the intermediate operator. I mean, I'm sorry, I cannot. Maybe I can write here, but it's not seen. So you introduce some intermediate states, but this is not just the product of the fog vacuum, you have to introduce a charge there. So this is the central charge you talked about. So this appears because the TBA equation has a zero mode in this limit, in the conformal limit, and any linear function of the rapidity passes through the TBA equation. And the coefficient in front of the linear term is this Liouville charge, which will change the central charge of the theory. So, yes. 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 Not the loops which you call loops. All different loops. So the same word is not for me. It would be very confusing to me. Let me see.
So can I suggest we carry on this discussion at coffee? And interesting though it is, but because we're running out of time.
They are the same loops. They are the same loops. They are the loops of the original theory, which I mean the particles of the original theory which wind around the torus. But the extra fields, these auxiliary fields, they are not loops. We integrate it around on the loops, and they are just they correspond to the scattering factors.
Okay, Chairman's prerogative. Thanks very much, Ivan.
Yeah, thanks.